All right, well, let's go ahead and get started. Well, so this is the last colloquium of the spring 2023 semester, and so we have two students talking. So Harrison Mausolff, who's going to, this is sort of his quasi thesis defense, and Dhan Bautista. Actually, they sort of previewed these talks already at the March meeting, and basically the Harrison's talk is actually going to be what his thesis is based on. And Dan's talk, we don't have an undergraduate thesis, but it's basically what his research with Dr. Vitali has been on. So without further ado, oh, I should mention, both of them are outstanding graduate student and outstanding undergraduate student. So we just turned that in. So congratulations, guys. That means you get to come to dinner for free. Well, you also get to come to dinner for free because you're a graduate. Anyway, so Harrison's going to tell us about his work in the Hartree-Fock approximation to the 2D Hubbard model. So Harrison, take it away.
Okay, thank you, Professor, and thank you everyone for showing up, and thank you the entirety of the physics department, both for allowing me to present this, but also for the education. It's really been a great experience. Right, so he already introduced my name, I don't need to do that. Just a quick little overview and table of contents about what I'm going to be talking about. Start really with a kind of basic background and motivation for these sort of research, and then a really nice conceptual introduction to what I'm going to be talking about. And then of course it's physics, we have to go through the actual mathematical introduction. I promise it won't be too bad. And then from there I'll actually introduce the Hubbard model, talk about the ways in which you actually solve it, how you can actually, once you have solved it in a sense, how do you actually analyze it, what are some of the results you get from it. And some of the more general methods, which is what I'll end with. And maybe at the end, if there's time, I'll talk with the thing that I talked about in the March meeting, this sort of application for something called QMC. But anyway, so it's always worth remembering that quantum mechanics is responsible for 90+% of the technological advancements of humans for the past 100 years or so. I can't think of any other science that really has advanced the world as much. Most specifically because of transistors, right? MOSFETs are the basis of all modern computing, but also in biophysics you have things like MRI machines. Not a biophysicist, I can't think of another one. But also more efficient lasers, that also has come from that. Material science, graphene, and eventually hopefully better battery technology as well. Now, for physicists though, all you really do when you're trying to develop and understand quantum mechanics in sort of a non-relativistic sense is how do you solve the Schrödinger equation? And really in sort of condensed matter, it really just boils down to what is the ground state of the system that I'm analyzing. That's really all you do. How bad could it be? Turns out it's a little harder than you think. So in principle, you would like to get to the true ground state of the system. That is, you set up your true Hamiltonian, you set it all up, you diagonalize it, you'd be good to go. The problem is that there are a lot of inter- and intra-atomic forces that you have to account for that basically make it unsolvable, even at the computational level. So for example here, you got like two metals here, just kind of show kind of the nuclei and sort of the valence electrons kind of running around. However, the best way to do this is always the joke that in physics we always start with the so-called spherical cow, right? You know, if you really tried to model the aerodynamics of a cow, let's start with the sphere. And that's really what a lot of what I'm going to be doing here today is, which is I'd like to really model a lattice of this particular metal. I can't, so I'm using a much simplified model, a much simpler lattice essentially. But again, you know, why am I doing this in specific with regards to physics? The actual goal of the thesis was to develop this code for solving the Hubbard model using Hartree-Fock methods. And then the plan was then to use a lot of that in conjunction with what Dr. Vitali does with something called quantum Monte Carlo simulations. And actually, it was to basically optimize that sort of methodology that we're using. In fact, I did a March meeting about some of the early research results that we did for that. Okay, now to get, again, more specific, how do you actually solve for the ground state in these so-called many-body problems? Many-bodied because we're no longer dealing with one electron in a box sort of thing. We're really dealing with many electrons with some sort of potential. In sort of condensed matter in atomic physics, we often talk about weakly correlated versus strongly correlated. The basic gist is weakly correlated is much easier, and strongly correlated requires a supercomputer a lot of the time. But we could correlate to things like Hartree-Fock, which I'm going to be talking about, but also density functional theory, perturbation theory is another one of these things. Strongly correlated, quantum Monte Carlo, and this thing called density matrix denormalization. It sounds fancy, I don't know what it means. Now, I want to go over the sort of background for the code that I developed, right, sort of the physics that you need to actually understand it and solve it. But there's a more basic question, which is what is that simple lattice? Or in this case, what is the actual Hubbard model? Conceptually, the Hubbard model is this nice picture here on the right. All the Hubbard model does is essentially ignore most of these interatomic forces and just look at the motion of the electrons in a very simplified way. We also account for the spin, but we'll get to that in a second. The only real positions that we allow for this sort of system are basically, it can only be at their particular sites. Basically, the sites are where the nuclei would be. So it only has these sort of distinct positions. So if I had 10 sites, the electrons can really only have 10 distinct positions, rather than, say, actually having spatial positions. And instead of the normal sort of interatomic forces, we just talk about the Coulombic repulsion instead. That's sort of the potential energy term that we talk about. Basically just Coulomb's law. Okay, but we got to go back a little bit. This is physics. I have to scare you a little bit with the proper Hamiltonians. This is really all the kinetic and potential energy terms of what they would look like in a sort of strict vector notation sense of n electrons with m nuclei. And as you can tell, and anyone who's taken more quantum mechanics knows, this is completely unsolvable and horribly impractical for getting any real meaningful results. Although here in the chemistry department they figure it out. Again, this is sort of the real true cow, not the spherical cow. Okay, so let's take a big step back. If this is quantum mechanics, I'm trying to develop the Hubbard model. Let me just start with a simple basis here. That is, I have one electron that has some position in space and it has a spin in the z direction of either up or down. That's all that little thing is telling me. Now, I want to get to many particles. So if I try to extend this into, say, just 2 electrons, it quickly becomes quite complicated. Fermi statistics tells you that you have this sort of minus sign, it's 1/√2, and if you kind of generalize this, it gets very complicated and the notation becomes even worse. And one of the tricks to get around this problem is to introduce something from quantum field theory, the so-called creation-annihilation operators. I'm not going to go too much into detail about these or even their algebra, I just put that there to satisfy the theorists here. But all these things mean in this case is, remember, I'm restricting the motions of the electron in this model to only jump around from site to site. Well, the creation-annihilation operators essentially do that. Basically, the one with the dagger is the creation one, and the one without the dagger is the annihilation, the one that destroys it. So the one on the right here, in specific, this one would destroy an electron at position R with spin up versus spin specific, and this would create it at that thing there. And then you just apply what you know about quantum mechanics, so you have to do the exclusion principle, all those sorts of things are naturally baked into these operators. Now, why include these at all? Well, if you remember the sort of basis that I introduced earlier, it's really easy to write with these operators. Instead of having to write all this bracket notation, you just write the vacuum state, and then you write your number of particles is basically equal to the number of creation operators. That's all that's doing there. And what that allows you to then do, and this will seem like a big jump in complexity, but this is how I learned it, so that's how you're going to learn it too, which is just to introduce the Hubbard model. Now, again, the conceptual introduction I talked about earlier is really baked into these 2 terms, right? So this first term here, this is like the kinetic energy. This is the term that is responsible for the actual hopping of the electrons. And this is the sort of cost, the sort of Coulombic force that I talked about earlier. Now, what do these things actually mean in principle? Again, the first term just takes an electron at position R prime, removes it, and then creates it at R. Notice sigma doesn't change. Obviously, you have to deal with the same spin. And then the interaction term, whatever it is, you want to call this one, potential energy term, it gets called all kinds of things. In this case, I'm going to call it the interaction term. It's doing the same thing, notice, right? The dagger just means it creates one. If it doesn't have a dagger, it means it destroys one. So if you can destroy one, then create one of two electrons with different spins but at the same position, there you're going to have some sort of Coulombic force, right? It's just simple basic physics, physics 4B sort of thing. How much energy do you pay? That's what we call U. This is again just sort of an energy cost. All you're doing is looking at electrons jumping around, and they pay a cost if two are at the same site. We don't account for any forces, say, between states. Why? Well, we'll see pretty shortly here. Now, again, the classic way when you're introducing a complicated thing in physics is you make it simpler. And it turns out actually it's very useful, both conceptually but also practically, to just look at the so-called non-interacting solutions. All that really means is I'm ignoring the potential energy term. Just to finish explaining it, all right, now get rid of it. And the reason why I'm going to do that is the method that I use to kind of create this to really create the matrix for the Hamiltonian. Again, a little bit of background. The eventual goal, right, is to explain the code I created. So everything I'm doing up here needs to be translatable to a computer. And making matrices is great. Differential equations is good, but matrices are better. And you'll see that when I actually introduce the potential energy term after it, you'll see that the process is identical, essentially. It takes Okay, so like I was hinting at there, you can calculate the matrix elements. This is a normal thing you learn in quantum mechanics. You basically just stick the Hamiltonian in between your two Rosenkets here. And then in practice, remember, I'm only looking at the motion of the electrons. If you remember, that first term only deals with the ability for the electron to hop. And so, this might look a little bad, but I promise it's not too bad. So if actually, this H here really is an electron for one spin in specific, and for this particular example of a 3x3 lattice. So how do you actually read this? How do you create this? Doesn't look that bad, right? It's just ones and zeros. I know they're -1, but I'll explain that in a second here. The first term, which I should probably have on here, if you remember, we should go back. You have this here. This controls the sort of ability for it to hop. And then you have this -t parameter. This thing is called the hopping parameter. For simple purposes, I'm just going to make it equal to 1. But what you'll find out is that you notice that basically all these elements then that aren't 0 are equal to -t, which in this case, like I said, from 1. How do you actually calculate this? You can do this by inspection. When I created this Hamiltonian, I did not solve this on Mathematica. I literally wrote this out in LaTeX, element by element. It sounds bad, but it's actually not. So for example, if you look at, let's take this element. So this would be 1, 2. What does that mean exactly? That means I'm an electron at site 1. Can I jump to site 2? Yes. Notice then that you can extend that to all the other elements, and that's all that first term is telling you to do. Now what that means is, and this is a subtle point that we may or may not get to, I'm assuming there were so-called periodic boundary conditions, and in this case all that means is that if I'm at site 1, I can kind of loop back around to site 7. If I'm at site 1, I can loop around to site 3. So if you're at 8, you go to 2, so on and so forth. And then if that's possible, again, you assign that -1 value. And this is just a side note. I tried to mention it before, but in principle, because of those creation annihilation operators, you can actually break up the true Hamiltonian for this one electron thing into this sort of separation matrices. That way you get this matrix, which would be for one electron with one spin, but if you wanted, say, 2, if you want to be able to account for all the spins, you'd also have to account for this sort of down matrix. But anyway, more importantly, and again I got another scary formula here, is I created a matrix. Computers are excellent at diagonalizing matrices, and you can get eigenvalues and eigenvectors, which is often all you're doing in basic quantum mechanics. But you might be thinking to yourself, well, this is a little bit of a problem. You just talked about one electron, and you said you wanted many electrons. So how do you deal with that? Well, you can get a ton of eigenvectors and eigenvalues whenever you just have this sort of one particle, what we call one-body matrix. It creates a bunch of these energy levels, and then if you want more particles, you just simply stick more particles in there, and then you calculate the so-called Slater determinant. It looks bad, but really all you're doing is, imagine each column as being a, remember it's one electron, so each column refers to that eigenvector for, say, one electron, and you just keep tacking on these column vectors for as many electrons as you want to actually deal with. And this actually turns out to give you something called the Slater determinant, which is just a wave function, but it's a way of calculating a wave function. Actually makes the whole thing in some ways a lot easier. Okay, but even then, it turns out it's a lot easier instead to look at something called the one-body density matrix. Very fancy name. It has this formal definition here. In practice, we use this formula. Okay, fine. But the important thing about this G matrix is that you can calculate stuff with it. And it just depends on that Slater determinant. Once you have your Slater determinant, you calculate G, and then you're good to go. And in specific, it's actually something called, I'll probably say this wrong, it's either Wick or Wick. Wick's theorem that actually allows you to compute the observable. So if you want to compute, say, the kinetic energy of the system, that depends only on the Hamiltonian, which remember, this notation means the matrix elements. So we have H, and then I have G. I already know all those beforehand. You can calculate the expected value of the energy. You can calculate the spin densities, which are relevant for things like phase transitions and stuff like that. But this is all great, and as always with physics, you showed me the easy one. What about when you actually consider the full model? What do you actually do? And it turns out that anything more than one dimension, the Hubbard model is impossible to solve. 1D you can solve it exactly, somewhat cleverly. And this is because of the potential energy term. It turns out to be just too complicated to really analyze and solve, and so we have to develop some sort of approximation method here. And in specific, I'm going to be looking at Hartree-Fock approximations. Now, Hartree-Fock does a bunch of substitutions. The important substitution comes from this n operator, right? The little n hat operator. That's just a particle density. Just tells you the number of particles at that particular site I. And the point is, you can replace this here, and you get this nice combination of particle operators. And you also need this relationship right here. That's really where the trick comes in. So yeah, if you actually replace all the operations and you use this definition, you replace everything, you're left with the expected value of n and this sort of delta n here. What does this delta n mean? It's the quantum fluctuations, but the whole point of the Hartree-Fock approximation is just to ignore those. Basically, we take all these terms that are quadratic, set them equal to 0, assume they're very small, so we can multiply small by small to get smaller, and then get rid of them again just by using that definition. And this is, I'm telling you, I promise, it is better. It doesn't seem like it's better because there are two big issues. One, you're still not really clear how to solve it, and also the fact that you're sort of, this expected value, right, if you remember, depends on the actual state. So you have your Hamiltonian set up, but the way in which you solve it depends on the solution. It's a classic problem in nonlinear dynamics. And the best way to approach this is to make a guess. And as we know mathematically, a guess is called an ansatz. Now, right here I have on the right-hand side is this thing that's a phase diagram of the Hubbard model. What does that mean? It tells you that as you change that u parameter and t, but who cares about t, and rho just depends on the number of particles. So all I care about is this u term and the number of particles. And then that's it, and that tells you the state of the system. So for example, it could be paramagnetic, which has this orientation of spins, antiferromagnetic, which looks like this, and ferromagnetic, which most people know, all the sort of poles are aligned, so to speak. And so that begs the question, I said make a guess, so what kind of ansatz do I use? Well, again, this chart from before tells me which one to actually use. So for example, if I'm in this region here, right, say u equals 4 and rho is 1, that's often called the half-filling or half-filled band or something like that. You are in the anti-ferromagnetic region, and therefore you should probably use an anti-ferromagnetic ansatz, or AFM ansatz. Now, the whole point, right, is that this expected value depends on the solution, so let's replace it with something that doesn't. And n here just means the number of particles. L, if you remember from the previous thing, is the number of sites. That 3 by 3 simple lattice, that's all that refers to. R is just something that depends you're summing over. Here, M, though, is a little interesting. M here is the magnetization. And the whole trick computationally, what you do is, you start off with a random magnetization. You just pick it, right? I'm literally on the computer. It's in Python. I give it a random number. And then I actually use something called the self-consistency method, which is start off with a random M, do all the whole thing I talked about with the non-interacting method. So, you know, create the Hamiltonian, diagonalize it, create the Slater determinant, and actually calculate observables. And compare those results to the initial thing that I started with. Meaning, I can calculate this magnetization by doing the process that I talked about earlier, and then I compare it to the magnetization I started with. This is called the self-consistency method, which makes sense. And that is the entire process. And I actually, made code that did this specifically. Here's kind of a result for that. So it's for that 3 by 3 lattice at u equals 4, and I'm expecting an anti-ferromagnetic phase. So it should look like that. Now it doesn't look quite as nice as that, but the point is, if you look, it goes to a positive spin density to negative to positive to negative, which is in principle the same sort of thing as you would see kind of conceptually. Okay, great. But what if I want to do different ansatz, like say ferromagnetic ansatz? It's the same method. Again, N and L are the same things I'm talking about, number of particles, number of sites. And then M here is that same magnetization that I'm going to calculate. Well, sorry, I start with a random one, and then I calculate it later. And the kind of funny part about this is if you get a result, it's kind of what it should look like. If it's ferromagnetic, then all the things are sort of a boring graph compared to before. Okay, this is the problem. As I'm using results that someone has already done to confirm the results I already have. Can't really use that for anything new, right? And so you need a much more general method. This is what's called unrestricted Hartree-Fock, which is instead of looking at this magnetization, why not just instead analyze the sort of particle density, expected value of particle density. You just pick something random, and you just let the system sort of run through its self-consistency method, compute this sort of expected value for n, and just see if it matches up. And this turns out to work exceptionally well. And one way to make sure, though, is to actually compare the results. So kind of an exciting graph here. So this is the AFM, so that's when I'm using that ansatz. And this is UHF. And with UHF, I just started with some random thing, and yet it gives me the identical results. Thus proving, at least in principle, well, not in principle, that it works quite well. And you can use it for whatever system you want, any particles you want. It's very open, very general, which is good. Yeah. Well, faster than I thought. Okay. This is all great, but this is a weakly correlated theory. And one of the motivations for this thesis and the code that I actually used to develop was it's very useful to have this Hartree-Fock code because I can use it in this more advanced method, this strongly correlated method, something called quantum Monte Carlo. I'm not going to go too much into detail about the mechanics of it. The point is that I can calculate this psi sub t is just a wave function. And so I want to use these Hartree-Fock wave functions, which I can get very easily. You've already seen the results. I can get the wave function, I don't care. And I can then do this sort of operation here with this operator. And in principle, if you repeat this infinitely many times, you get something that's very, very close to the true ground state. Okay, it sounds great. In practice, it doesn't work out that well. There's something called a sign problem. And so you introduce an approximation to control that. And the question is, okay, I've already introduced an approximation. Can I do a sort of self-consistency method where I start off with the Hartree-Fock wave function, plug it into this QMC machinery, generate some sort of feedback loop, and actually make QMC quite a bit more accurate. that's the hope. We're still sort of working on it. This is some of the results that I did and discussed in the March meeting. I'm not going to go too into depth. All these things mean, these are just different metrics, basically ways of measuring the accuracy between the sort of starting, the mean field one that I calculated and the QMC one. The blue line is sort of the Hartree-Fock one that varies over U. Remember that same U parameter. The green one is something called the natural orbitals. They're just from QMC, not a big deal. The sort of interesting thing, though, if you don't understand anything, is that we started off by running QMC at U equals 4, but we seem to get better results as in these metrics are lowest at lower U values for Hartree-Fock. Just kind of an interesting note here. I also looked at the energy and magnetization. The nice part about Hartree-Fock is that it really minimizes the energy quite well. And the magnetization, however, follows a similar story what I talked about before. I repeated this process with different boundary conditions, the same sort of story. If you're curious about more of these details, you can ask me later, but I'm not really sure. Okay. In conclusion, though, the Hubbard model needs approximation techniques due to this interacting term. I tried to show some of the development analysis of the Hubbard model using Hartree-Fock. I looked specifically at the AFM and ferromagnetic ansatz as well as the more general unrestricted Hartree-Fock UHF. There I also tried to show some of the results from the March meeting about optimizing QMC, and the big takeaway from that, like I said, which is it seems like you want to keep using the lower U value as your trial wave function for QMC. And then the hope in the future for a future student to make them suffer through is can this be solved using machine learning? And just a nice thank you slide I wanted to include. Special thanks to Dr. Vitale here, my advisor, and the entire physics department for being so amazing. It's been an honor. Thank you so much.
Well, thanks for a great talk, Harrison. So actually, let's do questions now. Hey, what's up, Joey? So ask questions. So I have.
Oh yes.
Let me start. So the sign problem you alluded to, what is that? So let me just preface it by in QCD, they also try to solve things on a lattice. And there's a sign issue whenever you try to put fermions on the lattice. There's like a doubling. Is it the same thing?
Yeah, very similar.
Oh, okay.
It's because of that, this thing where if you look at, you get this minus sign when you're, instead of adding states, you have that alternating sign. And that seems to cause problems.
Okay.
It sounds like it's the same sort of problem. Obviously, Dr. Vitale.
I mean, it's right.
It's an explosion of the variance. When you do Monte Carlo, you simulate random things. But everything works until the variance is finite, so they don't spread too much. When you have fermions due to the negative sign, you can prove that your error to signal ratio behaves exponentially with the size of the system. So the bigger the system, you get exponentially more variance in your estimate, which for bosons doesn't happen. I'm not sure it's the same issue that QCD people may be dealing with, but it's likely to be at least related.
Yeah, because in lattice QCD, whenever you put a fermion on the lattice, there's some problem, like errata. Do you recall?
I don't remember the details. No.
Okay, yeah, it's me neither, except that there's a problem.
But it might be, right, because it's fermions only.
Yeah, so actually, so with bosons, the lattice QCD is fine.
Right.
And the problem is that Monte Carlo relies on probabilities, and probabilities cannot be negative. When you have all those minus signs around, you are starting to force the game to treat something. So you need to use the absolute value. But when you use the absolute value, you remain with an average sign, because you have fluctuating objects with a different sign. If they cancel each other, you end up dividing by 0. That's another flavor to tell the story. It might be that QCD people are the same, but I don't know.
I'm going to run back and look it up after this talk. Okay, so more questions? I have another question, but the students should ask questions.
It's okay if they don't. I'll take it personally.
Okay, well, I'll do that.
Yeah.
I did,
So this is for a two-dimensional model?
Yes.
What about extending it to a three-dimensional model?
It's actually weird. I mean, 3 dimensions gets kind of more complicated. I think if you take the limit, it actually becomes easier to solve as you increase the spatial dimensions, which is really unintuitive. But yeah, I mean, you can do 3D, but it becomes much more complicated. And actually, using 2D is fine. Some of the results, even in the real world, work. So why not go with the easier thing? You don't use the real cap.
But the actual point would be that this model in the recent period is mostly like designed from the cuprates, where the physical system seems to be 2D because you have the copper oxygen plane. But you can do all you did in 2D with it.
Yeah.
Because there's non-interacting lattice points, so it doesn't matter. There's a sheet on top of another sheet kind of thing.
That's a good question. I mean, because I think in principle that he was saying that the cuprate is like a 2D thing, it acts like a 2D surface. So you should
Well,
model.
it's a layer thing, it's like a parking lot, but
They don't-
it is like mostly assumed that the most important physics happen on 2D. And the other ones are mostly like also wars where electrons jump back and forth.
Okay.
But it's a theory, might not be true.
Yes.
I got lost with the difference between n for particle density and n hat. What was that?
What are you talking about, like capital N versus the sort of operator?
No, little n hat, this one.
Oh, I'm not sure I follow you. Which part do you mean? Do you mean like the difference between this and this part right here? Or?
Somewhat earlier there was an n without a hat, without a hat.
A capital N?
I mean, there's capital N, and that's just the number of particles in the system. Are you talking about this N?
Okay. I thought there was a lower n without a hat, so why doesn't that need a hat?
Well, the hat is just to distinguish that it's an operator. That's all.
Oh, okay.
Yeah.
So I do have
Yeah.
a question. So there's something called the icing model, right? 1D icing, and basically where you can solve it exactly in 1D, right? And I know there's a 2D exact solution by Onsoccer, right, Manfred? And there's no 3D solution. But now for the Hubbard model, it seems very similar, but there's a 1D solution, but you can't do 2D or 3D. So is there, let me get something. So is there a relationship between the ice? What's the difference between the icing model? It sounds, I mean, from my understanding, it seems very similar, right?
Yeah, and actually, the image, there's an image I stole here in the presentation. You find the source of this image right above it's the icing model, because it looks very similar.
Oh, that's the icing model?
Well, no, it looks similar. It's like in the original image of this, it actually compares the icing model to the Hubbard model, because you say they're very similar. The big difference is you're accounting for position of the electrons now, which adds a whole other layer of complexity. So you can actually, I mean, there's no way in the icing model to kind of, I don't know, think about operators or things like that the same way we can here.
Well, in the icing model, the things don't hop from site to site, do they, or no?
No.
They don't know. That is classic. There is also the quantizing model. So the classicalizing model is sigma I, sigma j, but sigma I is just a number which can be plus minus. The quantizing model has a sigma I is a co-limit or a spin operator. And that's also not solvable in
And the throat is scratched. All right, other questions, comments? All right, let's thank Harrison for a great talk. So our next speaker is Dhan Bautista, is graduating this year. Again, also outstanding undergraduate student for us this year. And he's going to tell us about Hartree-Fock-Bogoliubov study of spin-polarized Fermi systems. Dan, take it away.
Okay, so before I start, I just want to thank Dr. Vitale again and the rest of the Fresno State Physics Department for all of the guidance that they've given me that I attribute to all of the success that I've had thus far. And my talk will be a bit more applied than Harrison's was, so without further ado. Okay, so with the turn of the 21st century came the development of quantum simulators, which are engineered many-body engineered many-body systems that function, or that, what is the word? That effectively simulates complex quantum phenomena. And of these systems is the ultracold atomic gas in the optical lattice. And this gained popularity because of its ability to simulate condensed matter systems, where the optical lattice, because of its periodic nature, emulates the periodic crystal potential that an electron may feel. And the cold atoms themselves, which we take to be fermions, they just represent the electrons that would be in a crystal. And so this is nice because it allows for a highly tunable experimental setting, which allows us to pretty much have a more broad parameter and phase space. And with condensed matter systems, we can perform mean field studies of the optical lattice so that we can have starting points for more robust, non-perturbative calculations, such as quantum Monte Carlo, and give those results to people who are actually in charge of an experiment so that they can, I guess, like probe their desired phase. Okay, so as I said earlier, the optical lattice is periodic, and so it can simulate condensed matter systems. And because it can do that, we can model it with the 2D Fermi-Hubbard model. Now, because Harrison already went over the Hubbard model, I'll just like skip an overview. But what we want to focus on here are attractive systems. And to have attractive systems, we have to ensure that the ratio between U and T is negative. And when we have an attractive system and equal amounts of spin up and spin down particles in our optical lattice, what comes out is that the up particles find and all of the up particles find and pair with a down particle within the lattice. And this phenomenon is known as Hubbard pairing, and the overall state of the system is now the superconducting Bardeen-Cooper-Schrieffer, or the BCS state. And this BCS state is characterized by a constant order parameter. And as the name implies, the order parameter tells you whenever you have some sort of order in your system. And in this case, if the order parameter is non-zero, we have a superconducting system, and if it was zero, I suppose you would just have a metal. And so what we want to do now is polarize the system. And what I mean by polarize is we want to create an imbalance between the spin ups and the spin downs. And to do that, we apply a magnetic field in the up direction to, flip some of the down spins to up spins, and therefore creating a spin polarization. And because we're applying a magnetic field denoted by H, we have to add a term to the Hamiltonian. And essentially what happens is, the system becomes polarized because of the magnetic field. And so a natural question to ask now is, how will these fermions pair with each other? Because now, we have an imbalance, so not all of the spins can find a pair. And as I stated earlier, when we have equal amounts of spin up and spin down, the ground state just becomes the BCS superconducting state with a constant order parameter. Now, in the case of unequal amounts of spin up and spin down, the solution is, a lot more complicated, but solutions were suggested by scientists Fold and Farrell, which I'll call the FF state, and Larkin and Ovchinnikov, which I'll call the LO state. And here, these states are characterized by spatially varying order parameters. And in this case, pairs still form, but in the BCS case, okay, let me go back to the BCS case. In the BCS case, pairs form between particles with equal and opposite momentum. So in total, for that Cooper pair, there is no center of mass momentum. But in the spin imbalance case, pairs form. But now, the Cooper pairs will no longer have a zero center of mass momentum. And they'll move with momentum given by Q. And Q right here, this is called the pairing wave vector and is proportional to the total polarization of the system. Okay, so one last complication to the Hamiltonian. We want to focus on spin-orbit coupling. So what spin-orbit coupling denotes is that whenever you have, let's call it a spin down. Whenever you have a spin down, there's a chance that while it moves, it can flip to be a spin up fermion, and vice versa for up to down. And the spin-orbit coupling is parameterized by this lambda here. And because we have spin-orbit coupling, now we have to add another term to the Hamiltonian. And so, again, spins are allowed to flip when moving throughout the lattice because of the spin-orbit coupling. Now, we have all of this. So what we have to do is choose the parameters we want to use for our simulation and determine how the system will behave with said parameters. And two studies have been performed, one by our very own Dr. Vitali and the other by his collaborator. And for the case on the left, we have zero spin orbit coupling, but with a non-zero spin polarization. And what results is an LO ground state, which I'll explain why in a bit. And on the other hand, we have the case of non-zero spin orbit coupling, but with no spin polarization, which results in a BCS ground state. And we can see this by looking at, well, these graphs. These are plots of the pairing correlation function. And at least for the LO state, this light blue is, light blue denotes positive values, and dark blue denotes negative values for the pairing correlation function. Now, because we have a sign change here, that implies that we have an LO ground state because of the trigonometric form of its order parameter. Now, on the other hand, for this side, we have a BCS ground state because if you notice, there is never a sign change taking place along the entire space. And so what I focus on is what happens when the spin-orbit coupling is non-zero and when we have a finite spin polarization. And so to tackle this, we have to tackle this Hamiltonian. And it's a bit of, well, in my opinion, it's a mess. So, believe me or not, these first three terms, they're pretty simple to deal with. They're easily diagonalizable, just because each one has a product of only two creation and/or annihilation operators. Now, as Harrison said earlier, the main big problems come from the interaction term right here. And this is because we have a product of 4 creation and annihilation operators. And so, really, what can we do, right? Well, we can do a Hartree-Fock-Bogoliubov calculation, which is pretty much just an extension of Hartree-Fock, which Harrison explained earlier, to independent pairs of fermions rather than just independent fermions. Now this is also just a mean field approximation, but it allows for the diagonalization of the entire Hamiltonian. Now, all of the information coming from the simulation is stored in two quantities. One is the one-body density matrix, which Harrison also went over, and the other is the pairing tensor. Now, how this works is we perform a mean field breakup of the Hamiltonian. So let's do that real quick. And this arguably looks worse. But it's actually a lot easier to deal with because now we have only a product of two of these operators in the interaction term. And every single term now only has to deal with a product of two. Now, in this mean field Hamiltonian that I have up here, I'm actually not showing two additional terms, but that's just because these two terms pretty much demonstrate the apparent phenomena that's taking place. And so what we do next is initialize the order parameter. And so here we choose what kind of phase we want to deal with. So with the constant order parameter, it's the BCS phase. The second one, the trigonometric order parameter, this is the LO phase, and this is the FF phase. Along with the order parameter, we also specify the spin polarization and the density of the system and the spin orbit coupling parameter. And then next, we choose a supercell shape, which is just the shape of the entire system, to accommodate the FF and the LO order parameters. And this is so that we can see the entire modulation of the of the order parameter along the system. For a BCS state, we can have any shape just because we have a constant order parameter. And then after that, we perform self-consistency, where we minimize the free energy of the system and calculate the system properties. And then we can just repeat the process for any of the phases that we want to investigate. Okay, so from this point on, I will just be showing results of the simulations that I've been running throughout this year. So first, we take a look at the energetics. And this will tell us what ground state the system chooses as a function of the spin-orbit coupling. So here we can see that the free energy decreases monotonically for every single phase as a function of the spin-orbit coupling parameter. But to determine the ground state, we need to only focus on the minimum of the free energy. And here we do see a phase transition taking place at some critical lambda. And let's take a look. So at lower spin-orbit coupling, we have an LO ground state. And at higher spin-orbit coupling, we have a BCS ground state. And on the right here, I just have the plots of the order parameter as outputted by the simulations. Here for the BCS, it's constant. For the LO, well, it's not a simple trigonometric function, which implies that, okay, we have some more than one, I suppose, pairing wave vector in the system. And in the FF, well, that's what it is. But we disregard it completely because in no value of the spin-orbit coupling parameter is the free energy minimum with the FF state. Okay. So here are the Fermi surfaces of the LO and BCS state. So at lower spin-orbit coupling, I have the LO, and at higher spin-orbit coupling, I have the BCS state. And that's because those are the ground states that the system chooses. Now here, I want to point out, okay, if we try to pair some particles along the Fermi surface of the spin down and LO, we can't really do that unless we add unless we add momentum, right? So that comes from the pairing wave vector. But in the case of BCS, we can't, because if we try, we see that there is some states that we can pair with for if we try to pair spin down and spin up. And this is due to some smearing taking place at the Fermi surface because of the spin-orbit coupling and the applied field. Okay. So this is the pairing wave function of, well, these are the pairing wave functions of the LO state. And here we see that pairing takes, singlet pairing takes place along the Fermi surface of the LO system. Now singlet just means we have opposite spins pairing with each other. And we see right away that also singlet pairing dominates the triplet pairing, either of the triplet pairing. And so really we just neglect the triplet pairing, that we neglect that triplet pairing can take place in an LO system. I do want to point out that there's some sort of structure taking place in this, the triplet down-down plot. But again, because it's infinitesimally small compared to the singlet pairing, we just neglect it. Now for the case of the BCS, we find that triplet pairing takes place, or no, that singlet pairing takes place along the entire, along the entire Fermi surface of both the down and the up particles, with peaks taking place at the nodes. And as we would expect for the triplet pairing wave functions, the up-up pairs mostly along the Fermi surface of only the up particles, and the down-down takes place mainly along the down particle Fermi surface. Okay, so all the results I've just showed you are with periodic boundary conditions. And so what we did afterwards was open up the boundary conditions and see, okay, how does that affect the system? Oh, also, these are the real space wave functions. I just thought they looked cool, so I'm putting them up there. Okay, so opening up the boundary conditions resulted in spin currents taking place along the edges of the system, at least for the BCS state. And for the LO state, we also have some sort of spin currents taking place, but as we can see, they're spatially modulated as we go through the system. And what's also interesting is that these peaks, they take place at the nodes of the LO order parameter. And we wanted to investigate more about what this could mean, or how the system is behaving with the open boundary conditions. Now, for the BCS state, as I showed, there was a spin current taking place along the boundaries. But how are all the particles behaving in terms of their density and their magnetic moment? So what happens is that the simulation of the BCS state, it pushes equal amounts of spin up and spin down to the edges of the system, and puts the excess spin up along the bulk of the system. And then for the LO case, at least in the magnetic moment, we once again have some spatially varying, or of course it's spatially varying, but we have peaks taking place at the nodes of the system. And in terms of the total density, I don't quite know what's going on. But again, it looks cool, so I showed it up there. And really, this is pretty much it. So just as a summary, I performed Hartree-Fock-Bogoliubov calculations to determine the ground state properties of spin-polarized Fermi systems as a function of the spin-orbit coupling. We find that at low spin-orbit coupling, the ground state is an LO phase with a spatially varying order parameter. And at high values of spin orbit coupling, we have a BCS phase, which just has a constant order parameter. And then opening up the boundary conditions revealed the presence of a spin current, as well as, well, other interesting properties of the system. And as for future directions, we've been investigating more about the spin current, trying to find topological phases, or at least what physicists call topological phases. And then right now we're feeding these results into quantum Monte Carlo. And that's the end of my talk.
Thanks for a great talk, Dan, and again, time for questions.
Is there a simple explanation for the difference of the triplet spin state for up, up, and down, down?
How do you mean?
I saw there was a difference when both, in the triplet state, when both spins were up or both spins were down. There was a, yeah.
Right here? Or which one?
Yeah, this one.
This one?
The middle and the right picture.
Oh, the middle and the right. Okay, so they're taking place at different places because of, oh, okay, that's this one. So this takes place here because this is along the Fermi surface of the particles. And so more up-up pairing takes place there. And on the other hand, this is along the Fermi surface of the down particles. And so more down-down takes place right here.
I was expecting a symmetry with both are up or both spins are down. Why is there a difference?
Because we have a, what was it? We have a spin-polarized system. We have more up than down, and we also have.
Yeah, we are breaking explicitly the symbol.
Yeah, there's a magnetic field, right? And that's what
And if you
determines.
send that to 0, they will go back to this.
Actually, I was also wondering, yeah, because the singlet state has, and then he's got the triplet state,
Sure,
triple state, and
now-
there's the other triplet state, which is a positive mixture.
Both with a field and against.
Right. But, so I had a question. So you're considering putting a magnetic field across this thing, right?
Yeah.
And so normally magnetic fields destroy superconductivity above some point. So I mean, like, right, there's a critical temperature, right, for type 2 superconductors. So I mean, are we able to see that in these things? Like as you tune the magnetic field up, suddenly it becomes non-superconducting?
Not really, because we don't tune the magnetic field directly. What we do is we select a desired polarization. And through self-consistency, that determines the value of the magnetic field that we have in the system.
Right, so you guys aren't like playing with magnetic field and say, let me turn it down, let me turn it up.
No, we just play with the spin polarization. Is that right?
But, well, so those new things like LO, FF were suggested like many, many years ago, as suggested for the possibility that for magnetic fields that are low enough, the system could reorganize its own superconducting behavior, like the way Cooper pairs are formed, so that it's consistent with having also a magnetic field. So we sort of know that if we take the magnetic field big enough, then
You break superconductivity.
yeah, because essentially most of the pairing is like this. If you have a magnetic field, the magnetic field will want to create this, so you don't pair anymore. But Falde, Ferrell, Larkin of Chinnikov suggested that if the magnetic field is not that big, so you're still in balance, but you still can create a lot of pairs.
So the system's still superconducting?
The system is still superconducting, but not in the BCS channel. So that the Cooper pairs acquire a finite center of mass moment too. So the BCS pairing is K minus K. Which is, if you get to the Fermi surface,
So like for the BCS thing,
you see here,
okay.
you cannot do a K minus K, because if you try to pick a spin down with K and look for spin up minus K, you end up in the black.
Okay.
So what the system very smartly succeeds in doing is to redesign the Cooper pairing mechanism so that K is coupled with minus K plus Q. And that Q, and you can see that, like, if you go from minus K to K, you need to go up a bit. And if you look at the order parameter, that precise Q is the one modulating the width. I find it very beautiful physics.
So
It
you're
was
not,
suggested in the 60s, I think.
So if you turn the magnetic field down, the Q goes to 0.
Yeah.
And you lose the momentum of the pairs.
Yes.
Do you also lose the spin current on the boundary?
The spin currents of the boundary has more to do with the spin-orbit coupling than with the magnetic field.
Because if you lose the magnetic field, you should go back to BCS, so you have 0 average momentum, so that current should go away.
Yeah, if you have spin-orbit, it depends. If you look at spin-resolved currents, so you have with spin-orbit coupling, you can create a BCS system where the spin-up, if you just look at spin-up, they circle like this. If you look at spin-down, they circle the opposite way. So as you say, the net current goes to 0.
Right.
But spin-resolved current is different from 0. If you break the symmetry through the magnetic field, you remain with a net.
Yeah.
And people are very interested for quantum computing because you can have 2 states, one like this and one like that. That can be your qubit 0 and 1. But also there seems to be some connection with Majorana's fermions or to topological physics there. So there is a bit of excitement there.
so even if Majorana fermions don't exist as a fundamental things, you can make them in.
Yeah, we have many expressions of them here.
Pete?
What's a Fermi surface?
Okay, so do you know about the Fermi energy? It's basically the extension to more than one dimension. Fermi energy.
More comment?
If there are no more physics questions, I would like to share a historical aside. Professor Fulde was my theory professor when I was an undergraduate in Frankfurt. And with Professor Farrell, I also had correspondence later.
They were in Frankfurt?
Fulde was,
Huh.
I think when he and Farrell, he was student or postdoc with Farrell. And later he became a professor in Frankfurt. So I had him as theory professor when I was undergraduate. And he examined me also for examination.
All right. So, other questions, comments? So if not, let's thank both speakers once again. And this concludes the colloquium for this semester.